Hi, everyone. I'm Guy. I'm a PhD student at Stanford. I'll be telling you about joint work with two excellent collaborators, Clement, who's a professor at Sydney, and Eric, a professor at UPenn. This is work we started together when we were at Simons for the sublinear algorithms program a year and a half ago, and is now the presentation you see here. The work is titled Instance Optimal Uniformity Testing and Tracking. The sort of problem we consider in this work is that of uniformity testing. It's an extremely foundational and well-studied task. So here we get samples from an unknown distribution, and we want to determine whether it's uniform or not. And we'll always assume that we know the number of elements, so we know k, but we don't know anything else about the distribution. Okay, so the goal is to accept if the distribution is indeed the uniform distribution over k elements, and reject if it's some notion of far. And this task is extremely foundational. It's if you look up any textbook or class or monograph on distribution testing, typically a lot of the time is spent on this. It's very well studied, and the techniques often translate to other tasks within distribution testing. Okay, the way I gave you, it's not fully formalized because I haven't actually told you under what conditions we reject, just some vague notion of farness. And the most well-studied way to formalize this task is to say that the rejection condition is such that you must reject if your distribution is epsilon far in total variation distance. This is so well studied that Clement's monograph on distribution testing has 7 possible algorithms for this task. 6 of the 7 are actually optimal. So we know that every testing for any tester for this task must use at least square root k over epsilon squared. 6 of these 7 actually get a matching upper bound. 1 is off by a little bit. Okay, so we actually know a lot of ways to get optimal uniformity testing if we're measuring optimality with respect to total variation distance. Okay, but a motivating question of this work is it the case that all distributions that are epsilon far from the uniform distribution are equally hard to test? Another way of phrasing this is TV distance a reasonable way with which to benchmark? And to get at this question, I want to use a visual example. So what I did here is I have 3 distributions that I'm not revealing to you just yet. One of those 3 is the uniform distribution. The other 2 are not. And now I encourage you to look at this and try to figure out which of these 3 is the uniform distribution and which 2 are not. And maybe think about how confident you are in your answer. I'll pause for a few seconds. Okay, when I see these, what I think is the one on the left seems pretty clearly not uniform because it has a single element that appears so many times that it would be quite unlikely in a uniform distribution that one element would appear that many times. But the other 2 distributions, at least to me, seem a little bit tricky to distinguish. Maybe you have a sense for which is uniform, which is not, but it's not so obvious. By the way, all of these have the same number of samples, and all of them are on the same domain size of 10. Okay, now these are the actual distributions I use to generate these samples. So the one on the right is the one that is actually uniform. And then, unsurprisingly, the one on the left has a single element that appears a lot of times in the distribution, which is then reflected in the sample. The one in the middle, it's has some elements that are a bit more frequent and some that are a bit less frequent, but it's kind of hard to tell just by looking at the sample. And a crucial point I want to make here is despite the fact that the one on the left was at least visually much easier to distinguish from a uniform distribution, both have the same total variation distance to uniform. Okay, so both the left and the right are equally far from uniform if we are measuring things with respect to TV distance, even though one of them seems much easier to distinguish from uniform distribution. And part of the goal of this work is to develop a notion that captures this intuition. So what we're going to want is some notion of instance optimal uniformity testing. Our accept condition is unchanged. We still want to accept if the distribution is actually uniform. But we now want our reject condition to be a little bit more fine-tuned to the particular distribution we're looking at. We want some notion of opt capturing how easy it is to distinguish a D from uniform. And we want to reject using essentially opt samples, kind of the minimum number of samples for the particular distribution D we happen to be testing, even if we don't know what it is. Okay, and the next question is exactly how we should define this notion of opt. I'm going to start with a first attempt, which is essentially the strongest possible notion you could have, which will turn out to not fully work here. But it's still worthwhile to think about why it doesn't end up working in our setting. So in this notion of opt, we're going to define it to be the minimum number of samples needed to distinguish the uniform distribution and this one distribution D. So this is a setting where a tester knows it's either getting uniform or D, and it only has to distinguish between these two. And then if we want an instance optimal tester, under this definition, we would want it to have the behavior that simultaneously for all distribution Ds, it can distinguish them with a number of samples that is competitive with this notion where it's competitive with what it would have if it knew D. Okay, now why does this not end up working as stated? Consider this case. So the case is going to be where a distribution is uniform over half the domain. So here are 3 examples of distributions that are uniform over 5 of the 10 elements. It turns out for this particular notion of opt, all of these have a constant opt. Using just a constant number of samples, you can distinguish them from the uniform distribution. If you knew, what the half, like which of these 3 distributions you had, like if you knew which half of samples D was uniform over. And the reason for that is quite simple. If I knew I had, say, the distribution all the way on the left, and I ever got an element that has 0 mass under that distribution, I would immediately know I'm in a uniform distribution. And if I never get any of those, that's quite unlikely under the uniform distribution. So there's a very simple test that just looks at are any of the elements that have 0 mass under D present in the sample. Okay, but the unfortunate thing with this definition of opt in this case is there is no single tester that distinguishes between the uniform distribution and a distribution on an unknown half of the domain. So like if I know the half, I can do it with a constant number of samples. But if I don't know the half, I need square root k many samples. And the reason for the square root k lower bound is quite simple. If I don't know which elements are special, essentially there's nothing I can do until I see a collision, until I see a particular element appear twice. And that takes roughly square root k many samples via the birthday paradox. This example is actually, very well understood. It's the reason for the lower bounds for uniformity testing I mentioned, roughly at the beginning of this talk. And it does end up defeating this particular notion of opt. So we're going to end up using a different one. And the notion we're going to define is essentially just going to get around this one case. And that will end up being enough. So we're going to define opt to be the number of samples, the best possible, taken by the best possible sampler, that distinguishes the uniform distribution in all ways of relabeling the elements of the domain. So in the case on the previous slide, it's like all ways of choosing a different half of the elements. This is a way of kind of capturing that opt should not allow the tester to cheat and kind of know which elements are special. And the reason this is a justified thing is, well, one, it's necessary, but two, uniformity is a task in which no element is special. Like they all have kind of the same meaning. And so it makes sense to try to think about testers that also don't treat any particular element as special cased, and instead should have the same behavior if you rename the elements. Okay, so as suggested, it defeats this particular example in the previous slide. And the reason is, if D is one of these 3, then when you consider the class of all relabelings of D, you now consider all distributions that are uniform over any half of the domain. And now opt would require you to be, to ask, what is the tester that best distinguishes between the uniform distribution and distributions that are uniform over an unknown half of the domain? And that takes square root k samples. And now we're competing with something where we have a chance. Now, it's not the case that you always get at least square root k. Remember, we had this intuition a few slides ago where when there's a heavy element, the task is simple. And that ends up being the case for this definition. So distributions with one heavy element end up having a constant opt. So this does get more at the sort of intuition, at least I had when I looked at the diagrams a few slides ago and trying to figure out which seem obviously uniform and obviously far from uniform. Okay, so now that we have our notion of opt, I can tell you our first main result, which is we give an instance optimal uniformity tester up to log factors. So it's a tester, a single tester. It doesn't need to know anything about the distribution it's testing, with the guarantee that it will with high probability accept the uniform distribution, and given n samples, for any distribution that could be tested with roughly n over log n samples, it rejects with high probability. So it, up to some logarithmic factors, it's actually a log n cubed, if I remember correctly in our result. This is an instance optimal notion of uniformity testing, where we defined opt to be this label invariant definition a slide ago. Okay, that is one of our two main results. I'm now going to give our second main result, which is essentially the same thing, just cast in a slightly different way. And that's going to be in a more online perspective, which we'll call uniformity tracking. So in this version, at each time step, we receive a single sample, and the algorithm at each step gets to make a choice. It either outputs reject, if at this point it's convinced via the samples it's seen so far that it is we're not receiving uniform samples, or it outputs plausible, in which case it says, what I've seen so far looks pretty uniform, let's continue going. And the guarantees we want are that if it is a uniform distribution, this tester will output plausible indefinitely. And if the distribution it's receiving samples from is not uniform, it will eventually output reject. And it will furthermore do this in a number of samples that is quite good, ideally as soon as possible. Now, one remark about this definition, the tester will never output accept. And it's not hard to see in this case, you have to design it in this way. If any tester ever outputs accept, I'm convinced it's uniform, you can show that it must be wrong. It cannot distinguish between a distribution that's uniform and one that's super, super close to uniform. And because you want a tester that works for every distribution, it will never know if it's taken enough samples to fully rule out every other distribution. Okay. Our second main result it looks very similar to the first. It's that this uniformity tracking is possible, and the number of samples you need is only polylogarithmically more than the optimal amount for just distinguishing all relabelings of D from the uniform distribution. Now, let me just say that this main result is it's like essentially equivalent in a very easy way to the first main result. So there's no new technical stuff happening here. But I think it's a nice perspective on what's happening, particularly in the instance optimal world. And let me explain like one nice consequence of this perspective, which is this tracker has a guarantee that if I ever receive something non-uniform, I will reject. And I will reject as fast as possible. The way we define as fast as possible is if I had rejected earlier, it would mean that I would be wrong either on the uniform distribution or on some relabeling of D. Okay, so it's kind of rejects as fast as possible with a nice excuse, like it must have been wrong in a slightly different setting, or like it must have been wrong on something we also want it to be correct on. Okay, now I'm just going to give a little bit of intuition for how we do this main result one, which, as I implied, via like pretty standard doubling arguments implies main result two. So you want this instance optimal uniformity tester. And that rejects that with high probability using n samples rejects if it were possible to test with roughly n over polylog n samples. Okay, so for this, I want to give some intuition via looking at what sorts of tests are optimal for different distributions. So one sort of distribution class that we want to like get a sense for what is optimal for is distributions that have half the elements being heavy and half the elements being light. And a particular object that will be useful in thinking about these uniformity testers is the frequency histogram. So what this is the frequency histogram is a way of representing a sample in a very concise manner that does not depend on the names, like on the labels of various elements. So in this particular histogram, what it's saying is it received a sample in which 5 elements appeared 0 times, 1 element appeared once, 3 elements appeared twice, and 1 element appeared 3 times. And we're going to design testers that only work on these frequency histograms. It turns out that's without loss generality to only look at this concise histogram representation. Okay, and it turns out that for this particular distribution type, where half the elements are heavy and half are light, one thing you can do, which ends up being optimal, is reject if there are too many elements that appear twice or more times. So in this case, there are 4 elements that appear twice, and we'd say, on the uniform distribution, there are 4 elements appear 2 or more times. And then we would say, on the uniform distribution, it's unlikely to have so many elements appear multiple times, and so I will reject. But that one tester does not work on all distributions. It's not always optimal. And now we have the other extreme, which has appeared continuously throughout this talk, where there is one heavy element. And it turns out on this particular distribution, the best test is to just look at the one highest frequency. And if that is high enough, reject. So we would say, on the uniform distribution, it is unlikely that any element appears 6 times. And so that's good enough information for me to reject. So these two, different types of distributions have different optimal tests, but both, compute some very simple statistic of this frequency histogram and then threshold it. And our main lemma, it's not this form we don't 100% prove, but is roughly speaking the main tool we use is to show that there always exists a test of this sort of form. So what we almost show is that for any distribution, there exists a range of frequencies, such that the optimal tester just counts how many elements appear a number of times in this range. And if that number is too large or too small, then the test rejects. We show that a test of this form is always close to optimal. Okay, once you have this result, we use what we call the interval tester, which all it does is it enumerates over all possible intervals. For each interval, it counts how many elements had a frequency within this interval. And if that number is too large or too small, it rejects. Okay, and one thing we use here is this is a tester that is enumerating over polynomially many things. It runs polynomially many tests on the back end. But when you want to union bound over polynomially many things via standard concentration techniques, that incurs only a logarithmic overhead in the sample complexity, which is crucial to our result, which gets only a logarithmic overhead. So our actual tester won't be just the interval tester. We need to do a few steps to get there. So, the first step we do, by the way, this slide will be very high level. Our paper has more details. Also, I guess, email me if you have more questions or find me at the conference. But okay, at a very high level, the way we transform to the interval tester is first we use a very standard technique, Poissonization, which is used to kind of reduce dependencies between the different frequencies. So we're gonna do one transformation to the frequency histogram. It turns out in our particular setting, for technical reasons, Poissonization does not allow us to say the frequencies are fully independent. So it's still a little bit hard to work with. The second step is something that is a bit more specific to our problem. Poissonization is a very general technique, is a decorrelation. So we show how to transform these possibly correlated frequency values into uncorrelated frequency values with slightly different structure. And then finally, when we have these uncorrelated frequency values, we then show that the interval tester works. Okay, that's very high level, 1, 2, 3, but I just wanted to kind of show you why we don't say the interval tester directly works, and we instead do some transformations to get it there. Okay, now, so closing, I just want to remind the audience that our main result is these uniformity testers and trackers up to log factors, and also just kind of introducing this notion of instance optimality in the regime of distribution testing and finding a good notion of opt for uniformity. And to me, I view this work as a very preliminary direction. This notion of instance optimality would be desirable for a lot of distribution testing problems, but there's quite a bit more work that needs to be done in other settings. The first question is, what is the right definition of opt for a particular problem? And for uniformity testing, we kind of had a notion for what would be best quite quickly, because uniformity testing is like very label invariant as a property. And so it seemed like a label invariant opt, if we could achieve it, would be great and reasonable. And we ended up achieving it up to logarithmic factors. But for other problems, maybe they have different sort of symmetry. And so you need different notions of opt that are reasonable for those settings. And then, for different notions, like some problems, even when you have a notion of opt that seems very reasonable, that they might not be possible to achieve them. There's other work that's not exactly stated in this way, but does imply some regions where what I would assume was a reasonable definition is still not achievable unless you lose poly factors rather than log factors. So I think there's still a lot to explore in this setting. Okay, thank you.